Welcome back to Abstract Algebra. In this video lecture, we're going to take a look at the main theorems in section 4.4. So I'm going to define for you something called a maximal ideal. We've been talking about ideals and rings. I want to tell you what I mean by a maximal ideal. And then I'm going to prove a theorem that will become the two parts of your author's theorem 4.4 and 4.42 and 4.43. All right, so that's really the goal of this lecture, is to prove those two theorems, although I'm going to state them as a single theorem, just making it kind of an if and only if. All right, so let's get busy here. We'll start with the definition. So we take some ring R, and we'll call an ideal in that ring maximal. So I'm defining what I mean by a maximal ideal. If I like to think of it as a two-condition checklist. Okay, so it's a maximal ideal if, well, first of all, it's not the entire ring. So the entire ring is never a maximal ideal. It has to be a proper ideal. And then the second condition is that whenever you have any other ideal that contains it, so you have some ideal that's containing M and it's an ideal in your ring, that other ideal is either M or R. All right. So another way to say this definition is that a maximal ideal is a proper ideal that's not properly contained in any other proper ideal. Okay, that's kind of a mouthful, but the not properly contained means that if M is, or sorry, if N is some ideal that's between M and R, then either N is M, so it's not properly contained in N, or N is R. But the only other ideal that really contains M properly is the whole ring itself. So in some sense, loosely speaking, it's like an ideal that's as big as it can be with respect to set inclusion that's not the entire ring. Okay, so this theorem I want to prove to you, it's not easy for me to explain why we want to look at this theorem. I'm kind of setting something up when we turn our attention towards polynomial rings. So this will be an important result for us when we go to look at a certain construction in polynomial rings. But maybe for right now, you can just kind of tell yourself that this is some chance to practice our ring theory. The proof of this theorem is not going to be terribly difficult. There aren't any kind of elaborate constructions that we have to make in order to get the theorem proved. However, it is going to be using tons of terminology, technical terms. We're thinking about things like fields and maximal ideals. It's a new definition. Okay, so let's just try to walk through it. I've kind of written the proof out already so that this video doesn't end up being too long. You don't have to watch me do a bunch of writing, but I do encourage you, as we're working through this, to stop this video a lot. I'm going to be making lots of statements, and you might need a little more time than what I'm going to give you just talking fast like I am right now. So stop the video as we're going and kind of digest these ideas as we go along. All right, I've rolled this into an if and only if theorem. Theorems 4.42 and 4.43 in your book together comprise the if and the only if statements here, the necessary and sufficient conditions. Okay, so let's take a look. What does the theorem say? It says if you take a commutative ring with unity, so we're going to be assuming that the multiplication in our ring is commutative and the ring has a 1, then an ideal in that ring is maximal if and only if the quotient by it is a field. All right, so I think Herstein's theorem 4.42 is that if M is maximal, the quotient is a field, and his 4.43 is if the quotient is a field, then M is maximal. I might be getting those backwards. I don't have my book open in front of me, but together he just splits this if and only if theorem into two. So the rest of this lecture is going to be devoted to proving this theorem. So let's get to let's get to work here. So let's start off by assuming that we have a commutative ring with unity, and we'll make the assumption that M is a maximal ideal in it. Okay, so our job is to show that the quotient ring R over M is a field. Let me remind you what a field is. What is a field? Well, a field is a commutative ring with unity. So we're going to have to show this quotient ring is a commutative ring with unity, and the unity element has to be different than the additive identity. And then we need to show that every non-zero element is invertible. Every non-zero element is a unit. That's the definition of a field. It's a commutative ring with unity in which each non-zero element has a multiplicative inverse. Okay, so we'll take those things one at a time. Let's start off on number 1. Okay, so we know that R over M is a ring because M is an ideal. And if the ring R is commutative, then if you take any two elements A and B and R, and you look at the product of the cosets containing A and B, by the definition of coset multiplication, that's the coset containing AB, but R is commutative. So AB is equal to BA, which is the product of these cosets. Yeah, B plus M times A plus M. So because R is commutative, the quotient ring is commutative. So good. What about the unity element? Well, R has a unity, right? And we made an agreement that when we talk about rings with unity, the unity element is never the additive identity. We don't have the trivial ring. So if you take any element in R and you multiply the coset containing that element by the coset containing unity, you end up getting the coset containing that element back. Do the product in either order. All right. So that shows that the coset containing unity is unity in the quotient ring. All right. Moreover, our ideal is not everything. A maximal ideal is always a proper ideal. And so unity doesn't belong to it, right? You can't have any units in a proper ideal. We proved it. So our unity element is not zero. This is the quotient ring way of writing this. Yeah, 1 is not 0 in this quotient ring. We write, well, unity 1 plus m is not m, right? The ideal m itself is the additive identity in the quotient ring. Cool. So that's half, in some sense, of our work, that we needed to show that this thing is a commutative ring with unity. But now we need to show that every non-zero element in it is a unit. So we've shown the quotient ring, we've shown the quotient ring is a commutative ring with unity. So we have to show that every non-zero element in the quotient ring is a unit, and that will complete the proof that this thing is a field. All right, so let's take a non-zero element. Let's take a non-zero element in the quotient ring. That is a coset that's different from M itself. And in particular, if that coset is different from M itself, then the element A can't belong to M, right? And now I define a set. I'm going to define a set N. And how do I define this set N? I take any ring element multiple of A. It's almost like I'm kind of forming the principal ideal generated by A, this A that's not in M. It's a specific element. And then I add to all those ring multiples of A everything in M, and I gather up the collection of all such things. Okay, so it's two parameters describing elements of this set. One is an arbitrary element of the ring R. I multiply it by A. The other one is an arbitrary element of M. I add it to that thing, gather up the set of all such things. I'm going to leave this as an exercise to you. I'm going to write it up and put it in a formal homework assignment, but you're going to prove that that set N is an ideal. It's an outstanding exercise for you to do, that set N is an additive subgroup of the ring R plus, and that it has the ideal property, the sticky property as we call it. All right, so I'm not going to say anything more about that. That's going to be your exercise coming up in homework 10. Or maybe homework 11, I'm losing count. Okay, so assuming that that exercise is done, it's an ideal, you're going to do your work. What do I care about that thing? If I choose the first parameter R to be 0, and then take an arbitrary M, I can see that M is an element of N. Yeah, M looks like 0A plus M. So every element of M is in N. So N is an ideal that actually contains our maximal ideal M. All right. If we take R, I'm just making strategic choices. If I take R to be 1 and M to be 0, then I can see that A belongs to N, right? A is 1 times A plus 0. But that element A we wrote above, it's not an element of M. So this ideal N properly contains M, right? Because I found an element, namely A, that's in N, but it's not in M. So that subset inclusion is proper. I just write that not equal sign under the subset symbol to emphasize that it's a subset, but they're not equal. All right? Well, M is a maximal ideal by hypothesis. We assumed M was maximal. So if you found some ideal, you're going to prove N is an ideal that properly contains M. That ideal has to be the whole ring. A maximal ideal, I'll say it again, is not properly contained in any proper ideal. So this N is properly containing M. It has to be improper. It has to be everything. Cool. Well, N has very specific element form, right? So I know that our ring R has unity. So unity must have the form Ra plus m for some r and some m. So there has to be some element r and some element m in our ring, in our ideal, so that 1 looks like that. Because 1 is an element of r, and r and n are the same set. So 1 has to have this form. So now let's just take a look at the coset. The coset containing 1, well, it's certainly the coset containing Ra plus m, because 1 is equal to Ra plus m. But little m is an element of m, so that coset is the same as the coset containing Ra, yeah? The little m, if you take the difference of those two things, that belongs to m. They're the same coset. And then by coset multiplication, I can write that Ra plus m as r plus m times a plus m. So what have I done? Let me let those lines go. The unity element in our quotient ring is equal to r plus m times a plus m. So that exactly means a plus m is a unit. I found its inverse. The inverse of a plus m is right there. It's the thing that you multiply by a plus m to get 1. Cool. A plus m was any non-zero element, and so we have succeeded. We have shown that r mod m is a field. Nice. I hope you stopped several times along the way to kind of absorb those steps. You can rewind this, read back through it, but it's an important argument for a young algebraist to absorb. Let's look at the flip side here. We have some more work to do. Now we're going to assume that this ideal M is in R and the quotient is a field. It's now going to be our assumption, and our goal is to show that M is maximal, right? Maximal ideals can't be improper. So first of all, if R over M is a field, then its unity element cannot be the additive identity. We forbid this. 1 is never 0. So that's enough to say that M isn't the entire ring, because it has at least 2 cosets. The coset containing 1 is different than the coset containing 0. So M can't be everything. So M is a proper ideal. So to complete the proof of maximality, we have to suppose if n is some other ideal that properly contains m, so I'm using my not equal sign there again to emphasize that those aren't the same set, but n does contain m, our goal would have to be, we have to show that n is actually equal to r. If we can show that the only ideal that properly contains m is the ring R itself, then m is maximal by definition, because we've already taken care of the fact that it's not improper. Okay, so that's our goal. Show n is equal to r. All right, well, let's see if we can do it. M is a proper subset of n. So there has to be some element that's in n, but not in m, right? Everything in m is in n, but there has to be at least one thing in n that's not in m, because m is a proper subset. So call that element a, and then its coset isn't 0. If A isn't in M, its coset's not 0 in this field, right? So if you have a non-zero element of a field, it has to have an inverse. I'm just calling its inverse B plus M. You could write A plus M inverse, but I'm just going to write B plus M. I don't want to write A inverse. I'm not claiming that A is a unit. I'm claiming that A plus M, the coset in the quotient ring, R over M, is a unit. Right? So there has to be some other element in the quotient ring that I multiply by a plus m to get 1. That's what it means to be a unit. Every non-zero element in R over M is a unit, because R over M is a field. Okay, well, if we do a little bit of arithmetic here, maybe I could help you. These product of these two cosets, that's A times B, plus M. And so if the coset containing AB is equal to the coset containing 1, then the difference of 1 and AB must be an element of M, which I'm reminding you is also an element of N, because every element of M is an element of N. All right? But the element A itself belongs to N, we said above. So I'm going to do a little bit of highlighting. If this element is in N, the element A, well, then the product of A times B is going to be in N. N is an ideal, right? So AB itself is in N. Let me write it somewhere. Oh, I did it. Well, I don't need to write it again. AB itself is in N. All right. Well, then add those two things together. If you add two elements of N together, you get an element of N, and those things add together to give 1. So we got one, unity is in N, and that forces N to be the whole ring. All right, so to recap, because R over M is a field, I was able to show you that M was a proper ideal, but the only ideal that properly contained it is the entire ring, and so M is maximal by definition. Cool. Nice. I hope that you stopped the video a lot while you were watching that proof to digest all those steps. We can talk about it again in a Zoom meeting class. I want to end, I don't want this video to be long. I'm going to keep it short, but we'll just look at a couple of examples from some of our previous work. You guys remember in class that we showed the ring of continuous functions quotiented by the ideal of functions that vanish at the number 1/2, the ring of continuous functions on the unit interval, excuse me. We showed that that's isomorphic to the field of real numbers with the first homomorphism theorem. All right, well, if this quotient ring is isomorphic to a field, then that means that that ideal is maximal. So the ideal that consists of all functions that are 0 at 1/2 is a maximal ideal. And more generally, I just want to sort of say this to some of you who might think this is interesting. There was nothing sacred about 1/2. You could take any number between 0 and 1 and look at the functions that vanish at that number, and you'll get a maximal ideal. And it's an interesting fact. Talk to me about this in an office hour or outside of that, even sometime if you want to, that every maximal ideal of the ring of continuous functions on the unit interval has this form. Every maximal ideal in that ring has the form, it's the set of functions that are 0 at some number. Yeah. So there's sort of a correspondence between maximal ideals in this ring and points in the interval 0, 1. A maximal ideal corresponds to all the functions that vanish at that point, and vice versa. And that is kind of the launching place of a subject you may have heard. It's called algebraic geometry. Algebraic geometry is a subject in which you try to encode geometric problems into an algebraic object so you can try to answer them. And here you're taking these points on an interval. Points in the interval from 0 to 1 correspond 1 to 1 with maximal ideals in this ring. So you can kind of study the interval by studying maximal ideals and vice versa. Yeah, so that's just sort of a little comment there to give you a flavor of what people mean when they talk about these subjects: algebraic geometry, algebraic topology, and so on and so on. In all of the cases, you're kind of trying to take some mathematical problem and encode it into some algebraic setting. Nice. You can ask me about that if that sounds interesting to you. When I was a student, and still to this day, stuff like that used to get me very excited because those two subjects seem to be very, very different, but they kind of have these hidden connections. Second example, last example, I just want to point out that the quotient of the integers, this is kind of a friendlier example, by the ideal generated by a number, well, it's equal to the ring of integers modulo that number. And we know that that's a field if and only if that number is a prime. Okay, so the ideals generated by P are maximal if and only if P is a prime. So we know in the ring of integers that it's a principal ideal domain. Every ideal has this form. And so now you know exactly which ones are maximal. Yeah, if you take ideals generated by primes, they're maximal. If you take ideals generated by things that aren't prime, they're not maximal. And maybe I'll just kind of illustrate with an example. This is not a maximal ideal. 6 is not a prime. So there must be some way to find an ideal, a proper ideal of Z that properly contains it, because I know it's not maximal. Can you guess what one would be? Maybe stop the video. I'm wondering, you know, all the multiples of 6 are properly contained in the multiples of something, but those multiples of something don't give me all integers. Yeah, because the integers, of course, are the ideal generated by 1. There's 2 possible answers here. Well, I guess 4 possible answers here, but maybe you were thinking something like this, that the ideal generated by 6 is contained in the ideal generated by 2. And those are proper containments. Not every multiple of, every multiple of 6 is a multiple of 2, but not every multiple of 2 is a multiple of 6, right? Like 4, for example. Cool. You could have also chosen the ideal generated by 3. In fact, those are the only 2 proper ideals that contain 6. Okay, thanks for listening.